As you sit reading these words, the universe is expanding around you. Every distant galaxy is racing away from our Milky Way at speeds that increase with distance. Their light stretched into longer, redder wavelengths by the expansion of space itself. This cosmic redshift, discovered by Edwin Hubble in 1929, revolutionized our understanding of the universe and revealed that we live in a cosmos that has been growing larger for nearly 14 billion years. But here's what makes this discovery deeply unsettling. Some galaxies are moving toward us. Not away. Their light arrives blueshifted, compressed into shorter, bluer wavelengths that seem to violate the fundamental principle of cosmic expansion. The Andromeda Galaxy, our nearest large neighbor, is approaching us at over 250,000 miles per hour and will collide with our galaxy in roughly 4.5 billion years. This isn't just one cosmic anomaly. Dozens of nearby galaxies show blueshift, creating a paradox that challenges our basic understanding of how the universe works. For nearly a century, we've built our entire cosmological framework on the assumption that redshift equals expansion, and that more distant objects recede faster according to Hubble's law. This relationship forms the foundation for our measurements of cosmic age, the discovery of dark energy, and our understanding of the Big Bang itself. Yet Andromeda's blueshift seems to mock this cosmic order, racing toward us as if expansion doesn't apply to our local cosmic neighborhood. The paradox deepens when we consider the implications. If the universe is expanding everywhere, uniformly stretching space itself, how can gravity overcome this expansion to pull galaxies together? The answer reveals a hidden complexity in cosmic expansion that most people never encounter. Story involving dark energy, gravitational binding, and the surprising discovery that cosmic expansion operates differently on different scales. Tonight, we're diving into one of the most elegant paradoxes in cosmology: how blueshifted galaxies reveal the true nature of cosmic expansion, the role of gravity in an expanding universe, and why understanding this paradox changes everything we thought we knew about space-time, and the ultimate fate of our cosmic neighborhood. Edwin Hubble's original observations in 1929 using the 100-inch telescope at Mount Wilson showed that distant galaxies display redshifts proportional to their distance. The farther away a galaxy, the faster it appears to recede. This Hubble's law seemed to indicate that the universe was expanding uniformly in all directions. But even Hubble noticed exceptions. Some nearby galaxies showed blueshift, including what we now know as the Andromeda Galaxy. These blue-shifted exceptions weren't measurement errors or observational flukes. Modern observations using the Hubble Space Telescope, the Spitzer Space Telescope, and ground-based observatories have confirmed that roughly 40 galaxies in our local group show blueshift, all within approximately 3 million light-years of the Milky Way. Beyond this distance, every observed galaxy shows redshift consistent with cosmic expansion. The explanation for this paradox lies in understanding that cosmic expansion doesn't operate like an explosion pushing objects apart through space. Instead, it represents the stretching of space itself, described by Einstein's general relativity and governed by a cosmic tug-of-war between the expansion of spacetime and the gravitational attraction between massive objects. In regions where matter density exceeds a critical threshold, gravity wins this cosmic battle, binding galaxies together into structures that resist expansion. Our local group containing the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller galaxies represents one such gravitationally bound system. Within this region, normal gravitational dynamics dominate, allowing galaxies to move toward each other despite the underlying expansion of space. The critical insight is that cosmic expansion operates primarily on scales larger than about 100 million light-years, where the density of matter falls below the threshold needed for gravitational binding. On smaller scales, the same gravity that holds solar systems and galaxies together can overcome expansion, creating islands of bound structure in an otherwise expanding universe. This understanding revolutionizes how we think about cosmic expansion and reveals the sophisticated interplay between general relativity, cosmology, and the mysterious dark energy that drives cosmic acceleration. The blue-shifted galaxies in our neighborhood aren't violations of cosmic expansion. They're proof that gravity and expansion operate simultaneously on different scales, creating the complex cosmic structure we observe today. The journey we're about to take will challenge your understanding of space-time, gravity, and cosmic expansion. We'll discover how Einstein's equations describe both local gravitational attraction and cosmic expansion simultaneously, why dark energy affects different regions differently, and how the fate of our local group reveals profound truths about the ultimate destiny of all structure in an accelerating universe. We'll explore cutting-edge observations from the James Webb Space Telescope that are revealing new blue-shifted galaxies in other galaxy groups. Investigate how computer simulations model the complex interplay between expansion and gravity. And uncover why understanding blue-shifted galaxies is crucial for measuring the Hubble constant and resolving the current crisis in cosmology. Most remarkably, we'll see how the presence of blue-shifted galaxies provides direct evidence for dark energy and cosmic acceleration. Since only in an accelerating universe would we expect to see such clear boundaries between bound and unbound cosmic structures, the same galaxies that seem to violate cosmic expansion actually provide some of our strongest evidence that expansion is real and accelerating. Now let's begin by understanding what redshift and blueshift actually represent, and why their discovery fundamentally changed our understanding of the cosmos itself. Light's journey. Light carries the most fundamental information about our universe, encoding in its wavelengths and frequencies the stories of distant stars, galaxies, and the expansion of space itself. To understand why some galaxies are blue-shifted while others are redshifted, we must first understand how light behaves as it travels across cosmic distances and how this behavior reveals the motion and de-evolution of the universe around us. When astronomers speak of redshift and blueshift, they are describing changes in the wavelength of light that occur when the source of that light is moving relative to the observer. This phenomenon, known as the Doppler effect, is familiar from everyday experience. The changing pitch of a siren as an ambulance passes, or the way a train whistle drops in tone as the train moves away from you. Light behaves similarly, with wavelengths stretching toward red when sources recede and compressing toward blue when sources approach. But cosmic redshift involves more than simple Doppler motion. In an expanding universe described by Einstein's general relativity, space itself stretches as light travels through it, causing wavelengths to increase even when galaxies aren't moving through space in the conventional sense. This cosmological redshift fundamentally differs from the classical Doppler effect and reveals the dynamic nature of spacetime itself. The discovery of cosmic redshift began with spectroscopy, the analysis of light broken into its component wavelengths, revealing the characteristic signatures of different chemical elements. Every element emits and absorbs light at specific wavelengths determined by quantum mechanics. Hydrogen, the most abundant element in the universe, produces a distinctive series of spectral lines at precise wavelengths that serve as cosmic fingerprints. When Vesto Slipher first observed the spectra of spiral nebulae in the early 1910s, he noticed something extraordinary. The spectral lines were shifted from their expected laboratory wavelengths. Most were shifted toward longer, harder wavelengths, indicating recession, but a few, including the Great Nebula in Andromeda, showed shifts toward shorter, bluer wavelengths, indicating approach. Edwin Hubble's breakthrough came from combining Slipher's redshift measurements with his own distance measurements using Cepheid variable stars as standard candles. Hubble discovered that redshift increased systematically with distance, leading to his famous law: the recession velocity of galaxies is proportional to their distance from us. This relationship implied that the universe itself is expanding, with space stretching uniformly in all directions. The mathematics of cosmological redshift emerges from Einstein's field equations applied to the geometry of an expanding universe. In the Friedmann-Lemaitre-Robertson-Walker metric that describes cosmic expansion, light wavelengths stretch by a factor equal to the ratio of the universe's size when the light is received to its size when the light was emitted. This stretching occurs continuously as light travels through expanding space. For nearby galaxies, the distinction between cosmological redshift and Doppler redshift becomes crucial. The Doppler effect depends on relative velocity through space, while cosmological redshift depends on the expansion of space itself. In practice, both effects can operate simultaneously, creating complex patterns of redshift and blueshift that require careful analysis to interpret correctly. The local group of galaxies provides a perfect laboratory for studying these effects. Within this gravitationally bound system, galaxies move through space under the influence of mutual gravitational attraction. These peculiar velocities motions relative to the cosmic expansion flow can overcome the underlying cosmological redshift for nearby objects, producing the blueshifts we observe. Andromeda's blueshift of approximately 0.1, meaning its spectral lines are shifted by about 0.1% toward shorter wavelengths, indicates an approach velocity of roughly 300 kilometers per second relative to the Milky Way. This velocity far exceeds what we would expect from cosmic expansion at Andromeda's distance, confirming that gravitational attraction dominates over cosmic expansion within our local group. The precise measurement of redshifts and blueshifts requires sophisticated spectroscopic techniques that can detect wavelength shifts smaller than the width of individual spectral lines. Modern instruments can measure redshifts to precisions of better than 1 part in a million, allowing astronomers to detect even tiny velocity differences between cosmic objects. These measurements reveal the complex velocity structure of our cosmic neighborhood. While the overall pattern follows cosmic expansion, with more distant galaxies showing larger redshifts, local gravitational influences create a complex web of peculiar velocities that can either enhance or reduce the cosmological redshift signal. The study of these peculiar velocities provides crucial information about the distribution of matter in the universe, including dark matter. Computer simulations of cosmic structure formation predict specific patterns of galaxy motions based on the underlying dark matter distribution, and observations of redshifts and blueshifts allow astronomers to test these predictions and map the invisible cosmic web. Understanding light's journey through an expanding universe also illuminates the relationship between distance and time in cosmology. When we observe a galaxy with a redshift of z=1, we're seeing light that was emitted when the universe was half its current size. The redshift directly measures the expansion factor of the universe between emission and reception, providing a direct probe of cosmic evolution. This time-distance relationship means that observing galaxies at different redshifts allows us to study the history of cosmic expansion by measuring how the Hubble constant changes with redshift. Astronomers discovered that cosmic expansion is accelerating, driven by the mysterious dark energy that comprises roughly 70% of the universe's total energy density. The precision of modern redshift measurements has revealed subtle effects that test our understanding of general relativity and cosmology. Gravitational redshift: the stretching of light as it climbs out of gravitational wells contributes to the observed redshift of galaxies embedded in massive dark matter halos. These effects must be carefully modeled to extract accurate information about cosmic expansion. The future of redshift studies lies in large-scale spectroscopic surveys that will measure redshifts for millions of galaxies, creating three-dimensional maps of cosmic structure with unprecedented detail. Projects like the Dark Energy Spectroscopic Instrument DESI and the Euclid Space Mission will use redshift measurements to probe the nature of dark energy and test theories of cosmic acceleration. Light's journey from distant galaxies to our telescopes thus carries information about cosmic expansion, local gravitational effects, the distribution of dark matter, and the mysterious dark energy that drives cosmic acceleration. The apparent paradox of blue-shifted galaxies in an expanding universe resolves into a sophisticated understanding of how different physical processes operate on different scales to create the complex cosmic structure we observe today. The wavelength of light becomes a cosmic clock and ruler simultaneously, measuring both the expansion history of the universe and the gravitational dynamics that govern structure formation. This dual role makes redshift and blueshift measurements among the most powerful tools in modern cosmology for understanding both the past and future of our universe. Expanding space: the expansion of the universe represents one of the most counterintuitive concepts in modern physics. Space itself grows larger, stretching the very fabric of reality and carrying galaxies apart without the galaxies actually moving through space. Understanding this cosmic expansion is crucial for resolving why some galaxies can approach us in an expanding universe. Because expansion operates fundamentally differently than we experience in everyday life. Most people initially imagine cosmic expansion as an explosion, with galaxies flying apart through empty space like debris from a cosmic bomb. This mental model, while intuitive, is completely wrong. The Big Bang wasn't an explosion in space, it was the beginning of space itself. And the ongoing expansion represents the continued stretching of spacetime geometry according to Einstein's general relativity. To visualize this stretching, imagine a balloon being inflated with dots drawn on its surface. As the balloon expands, The dots move apart from each other, but not because they're sliding across the balloon's surface. Instead, the surface itself stretches, carrying the dots along. Similarly, cosmic expansion stretches three-dimensional space, carrying galaxies apart without the galaxies moving through space in the conventional sense. The mathematics describing this expansion comes from Einstein's field equations applied to the geometry of the universe as a whole. The Friedmann equations, derived by Alexander Friedmann in the 1920s, describe how the scale factor of the universe, essentially its size, changes over time in response to the matter and energy it contains. These equations reveal that cosmic expansion depends on the universe's total energy density and its composition. Matter and radiation tend to slow expansion through gravitational attraction, while dark energy characterized by negative pressure drives accelerated expansion. The current universe contains roughly 5% ordinary matter, 25% dark matter, and 70% dark energy, leading to accelerated expansion that began roughly 5 billion years ago. The expansion rate at any given time is characterized by the Hubble constant, which relates recession velocity to distance through Hubble's law of v equals h times d, where v is recession velocity, h is the Hubble constant, and d is distance. Current measurements place h at approximately 70 kilometers per second per megaparsec, meaning that galaxies separated by 3.26 million light-years recede from each other at 70 kilometers per second due to expansion alone. This expansion rate might seem small, 70 kilometers per second over more than 3 million light-years, but it accumulates over cosmic distances. At 1 billion light-years, expansion drives recession at about 20,000 kilometers per second, or roughly 7% of light speed. At 10 billion light-years, recession approaches light speed itself, creating the cosmic horizon beyond which we cannot observe more distant objects. The crucial insight for understanding blueshifted galaxies is that cosmic expansion doesn't operate uniformly on all scales. Just as surface tension can prevent small portions of an expanding balloon from stretching, gravitational attraction can prevent small regions of space from participating in cosmic expansion. The strength of this gravitational binding depends on the local density of matter compared to the critical density needed to halt expansion. The critical density for the universe as a whole is approximately 9.5 times 10 kilograms, m, equivalent to about 6 hydrogen atoms per cubic meter of space. Regions with matter densities significantly above this critical value can resist expansion and form gravitationally bound structures. Our local group has an average density roughly 100 times the critical density, allowing gravity to dominate over expansion within our cosmic neighborhood. This creates a hierarchical structure where expansion operates differently on different scales. On scales larger than about 100 million light-years, the typical size of galaxy superclusters' matter density falls below the critical threshold, and cosmic expansion dominates. On smaller scales, gravity can overcome expansion, binding galaxies into groups and clusters that evolve according to Newtonian dynamics rather than cosmological expansion. The transition between these regimes isn't sharp but gradual, creating complex dynamics where expansion and gravitational attraction compete. Computer simulations of cosmic structure formation reveal that this competition produces the cosmic web, a vast network of filaments and voids where matter flows from low-density regions, undergoing expansion into high-density regions, collapsing under gravity. Understanding cosmic expansion also requires distinguishing between different types of horizons that limit our observations. The particle horizon defines the maximum distance from which light has had time to reach us since the Big Bang, currently about 46 billion light-years, despite the universe being only 13.8 billion years old, due to the expansion of space during light's travel time. The event horizon defines the maximum distance from which light emitted today will ever reach us in an accelerating universe. Due to dark energy, this event horizon is approximately 17 billion light-years away, meaning we can never receive signals from galaxies beyond this distance, even given infinite time. This creates a fundamental limit to the observable universe in an accelerating cosmos. The accelerating expansion driven by dark energy has profound implications for cosmic structure formation and the fate of bound systems like our local group. As expansion accelerates, the critical density threshold for gravitational binding gradually increases, meaning that progressively denser structures are required to resist expansion. This process will eventually isolate all gravitationally bound systems from each other. Current observations suggest that our local group will remain bound indefinitely, even as cosmic expansion accelerates. However, larger structures like the Virgo supercluster, of which our local group is a member, will eventually be torn apart by acceleration. In roughly 100 billion years, galaxies beyond our local group will have been carried so far away by expansion that they will no longer be visible to observers in the Milky Way. The measurement of cosmic expansion has become one of the most active areas of observational cosmology, driven by the discovery of dark energy and the need to understand cosmic acceleration. Type Ia supernovae serve as standard candles for measuring distances to high redshifts, while gravitational lensing and boron acoustic oscillations provide independent probes of expansion history. These observations have revealed subtle deviations from simple uniform expansion that provide clues about the nature of dark energy. If dark energy represents Einstein's cosmological constant, expansion should follow a specific mathematical form. Alternative theories of dark energy, such as evolving scalar fields or modifications to general relativity, predict different expansion histories that can be tested observationally. The expansion of space also affects the propagation of gravitational waves, stretching their wavelengths just like electromagnetic radiation. The recent detection of gravitational waves from merging black holes and neutron stars has opened new windows for studying cosmic expansion, potentially providing independent measurements of the Hubble constant that don't rely on electromagnetic observations. Understanding cosmic expansion as the stretching of space itself, rather than motion through space, resolves the apparent paradox of blueshifted galaxies in an expanding universe. Expansion provides the cosmic backdrop against which gravitational dynamics operate, creating a universe where local gravitational attraction can overcome cosmic expansion, while global expansion continues to stretch space on the largest scales. This sophisticated interplay between expansion and gravity creates the rich cosmic structure we observe. From bound galaxy groups like our local group to the vast cosmic web spanning billions of light-year rupees, the blue-shifted galaxies in our neighborhood aren't violations of cosmic expansion, they're proof that gravity and expansion operate simultaneously to create the complex cosmos we inhabit. Gravity's battle in the cosmic arena, where expansion and gravity wage their eternal battle. The outcome determines whether structures remain bound together or get torn apart by the stretching of space itself. This fundamental conflict shapes everything from the orbits of planets to the fate of galaxy clusters. And understanding this battle reveals why some galaxies can approach us even as the universe expands around them. The battle between expansion and gravity isn't a simple tug-of-war between opposing forces. Instead, it represents two different aspects of Einstein's general relativity operating simultaneously: the global geometry of spacetime described by the Friedmann equations, and the local curvature created by concentrations of mass and energy described by the full Einstein field equations. General relativity tells us that massive objects curve spacetime around them, creating the gravitational effects we observe. The stronger the gravitational field, the more pronounced this curvature becomes. In regions where matter density exceeds the critical density needed for cosmic expansion, this local curvature can overwhelm the global expansion, binding matter together into stable structures. The mathematics of this battle involves comparing two characteristic timescales, the expansion timescale and the gravitational collapse timescale. The expansion timescale, roughly equal to the age of the universe divided by the Hubble constant, represents how long it takes cosmic expansion to significantly change distances between objects. The gravitational timescale represents how long gravity takes to pull objects together over the same distances. For our local group, the gravitational timescale is much shorter than the expansion timescale. The Milky Way and Andromeda galaxies are gravitationally bound with a binding energy that far exceeds the expansion energy trying to pull them apart. This is why Andromeda approaches us at 300 kilometers per second. Despite the underlying cosmic expansion, gravity has won the local battle decisively. The critical factor determining the outcome of this battle is the density parameter, often denoted by the Greek letter omega. This parameter compares the actual matter density in a region to the critical density needed to halt expansion. When omega greater than 1, gravity wins and structures collapse. When O1, expansion wins and structures get stretched apart. When omega equals 1, the two effects exactly balance, creating a delicate equilibrium. On cosmic scales, the universe as a whole has omega very close to 1, with matter, and dark energy contributing to bring the total density parameter to approximately unity. This near-critical density means the universe expands but at a gradually decreasing rate at least until dark energy began dominating roughly 5 billion years ago, causing expansion to accelerate. But on local scales, density parameters can vary dramatically. Galaxy groups like our local group have omega values of 100 or more, meaning gravity completely dominates over expansion. Individual galaxies have even higher density parameters, which is why stars within galaxies maintain stable orbits despite cosmic expansion. Even our solar system has such high local density that expansion effects are completely negligible. This creates a hierarchical structure in the universe where different scales experience different outcomes in the battle between expansion and gravity. Planets remain bound to stars, stars remain bound within galaxies, some galaxies remain bound in small groups. But larger structures like superclusters eventually succumb to cosmic expansion as dark energy drives acceleration. The transition between bound and unbound regions isn't sharp but gradual, creating complex dynamics in the cosmic web. Matter flows from low-density regions that expand faster than the cosmic average into high-density regions that expand slower or collapse under their own gravity. This flow creates the filamentary structure we observe on large scales. Computer simulations of cosmic structure formation reveal how this battle plays out over cosmic time. Starting from tiny density fluctuations in the early universe, regions with slightly higher density expand more slowly, allowing gravity to enhance the density contrast. Over time, these regions stop expanding and begin collapsing, forming the dark matter halos that host galaxies and galaxy groups. The dark matter component plays a crucial role in this battle because it interacts gravitationally, but not electromagnetically. Unlike ordinary matter, dark matter doesn't experience radiation pressure or other non-gravitational forces that could oppose gravitational collapse. This allows dark matter to form the scaffolding of cosmic structure, creating gravitational wells into which ordinary matter flows. Within our local group, dark matter dominates the total mass budget, providing the gravitational binding that keeps the group intact. The Milky Way sits within a dark matter halo with a total mass of roughly 1 trillion solar masses, while Andromeda's halo contains about 1.5 trillion solar masses. These massive halos ensure that our local group will remain bound even as cosmic expansion accelerates. The discovery of dark energy has fundamentally altered our understanding of this cosmic battle. Dark energy acts like a repulsive force with constant energy density, meaning its effects grow stronger as the universe expands and the volume of space increases. This accelerating expansion makes it progressively harder for gravity to form new bound structures and may eventually overcome gravitational binding in all but the most tightly bound systems. Current observations suggest that galaxy clusters with masses above about 10 solar masses can remain bound indefinitely, while smaller structures may eventually be disrupted by accelerating expansion. Our local group, with a total mass of roughly 5-10 solar masses, appears to be comfortably above this threshold and should remain bound throughout the cosmic future. The battle between expansion and gravity also affects the formation of cosmic structure over time. In the early universe, when matter dominated over dark energy, gravitational collapse was easier and larger structures could form. As dark energy began dominating cosmic dynamics roughly 5 billion years ago, structure formation became increasingly difficult. And we now live in an era where cosmic structure formation is winding down. This cosmic evolution means that the bound structures we observe today, galaxy groups, clusters, and superclusters, represent the culmination of billions of years of gravitational collapse fighting again. Same cosmic expansion. Future epochs will see these structures evolving internally but becoming increasingly isolated from each other as expansion carries unbound matter away. The precise balance between expansion and gravity in different regions provides crucial tests of our cosmological models. By observing how galaxy groups and clusters evolve over time, astronomers can measure the growth rate of cosmic structure and test theories about dark matter, dark energy, and modified gravity. Recent observations have revealed subtle discrepancies in the growth rate of cosmic structure compared to predictions based on the cosmic microwave background. These tensions might indicate new physics beyond the standard cosmological model or could reflect systematic errors in observations. Understanding the battle between expansion and gravity is crucial for resolving these issues. The future evolution of bound structures depends sensitively on the nature of dark energy. If dark energy remains constant corresponding to Einstein's cosmological constant, bound systems like our local group will remain stable indefinitely. If dark energy grows stronger over time, it could eventually overcome gravitational binding in all structures, leading to a big rip scenario where the universe expands so rapidly that even atoms get torn apart. Current observations favor a constant dark energy density, but the precision isn't sufficient to rule out slowly evolving dark energy. Future surveys will measure the expansion history of the universe with unprecedented precision, potentially revealing whether dark energy is truly constant or evolving in ways that could affect the long-term stability of bound structures. The battle between expansion and gravity thus shapes not only the current structure of the universe but also its ultimate fate. Understanding this cosmic conflict reveals why blueshifted galaxies exist in an expanding universe and illuminates the fundamental physics governing cosmic evolution from the Big Bang to the far future. In this battle, gravity may win local skirmishes, but cosmic expansion appears destined to win the ultimate war. Local universe or cosmic neighborhood. The local group of galaxies represents a gravitationally bound island of structure in the expanding ocean of space-time, a region where normal gravitational dynamics dominate over cosmic expansion and create the complex orbital dance that brings some galaxies toward us rather than away. Understanding the local group reveals how cosmic structure emerges from the battle between expansion and gravity on the scales we can study in greatest detail. The local group spans roughly 10 million light-years and contains over 100 galaxies, though only 3 qualify as large spiral galaxies: the Milky Way, Andromeda M31, and the Triangulum Galaxy M33. The remaining members are mostly dwarf galaxies, small, faint systems that orbit the larger galaxies like cosmic satellites. This hierarchical structure reflects the gravitational organization that emerges when matter density exceeds the critical threshold needed to resist cosmic expansion. The total mass of the local group approaches 510 solar masses, with roughly 85% consisting of dark matter that we can detect only through its gravitational effects. This enormous dark matter content provides the gravitational glue that binds the group together and creates the potential wells in which the visible galaxies formed and evolved. Without dark matter, the local group would never have formed, and cosmic expansion would have prevented galaxy interactions entirely. The dynamics of the local group follow Newtonian mechanics rather than cosmological expansion, because the system's high matter density allows gravity to completely overcome the Hubble flow. Within this bound region, galaxies move under their mutual gravitational attraction, creating complex orbital patterns that can bring galaxies together despite the expansion of space. Beyond the group's boundaries, Andromeda's approach toward the Milky Way at 250,000 miles per hour represents the most dramatic example of this local gravitational dominance. Computer simulations based on the observed positions and velocities of both galaxies predict that they will merge in approximately 4.5 billion years, creating a giant elliptical galaxy that astronomers have dubbed Milkomeda. This merger will fundamentally reshape our cosmic neighborhood while the rest of the universe continues expanding around us. The Triangulum Galaxy adds complexity to this three-body gravitational system. Current observations suggest that M33 is probably bound to Andromeda, orbiting the larger galaxy at a distance of roughly 750,000 light-years. When Andromeda and the Milky Way merge, M33's fate becomes uncertain. It might be ejected from the system, absorbed into the merger remnant, or settle into a stable orbit around Milkomeda. The smaller satellite galaxies of the local group reveal additional layers of gravitational organization. The Milky Way hosts over 50 known satellite galaxies, including the famous Large and Small Magellanic Clouds visible from the southern hemisphere. Andromeda has its own retinue of satellites, while even some of the larger dwarf galaxies host their own smaller companions. These satellite systems demonstrate that gravitational binding operates across a wide range of scales within the local group. The most massive satellite galaxies, like the Large Magellanic Cloud with roughly 20 billion solar masses, are themselves substantial systems that could exist as independent galaxies in other cosmic environments. Their capture and retention by larger galaxies illustrates the hierarchical nature of structure formation in gravitationally bound regions. The discovery of the local group's gravitational binding required careful measurement of galaxy velocities and distances throughout the 20th century. Early observations revealed that most nearby galaxies showed blueshifts rather than the redshifts expected from cosmic expansion, providing the first evidence that local gravitational effects could overcome cosmic expansion in sufficiently dense regions. Modern observations using the Hubble Space Telescope have refined our understanding of local group dynamics by measuring proper motions, the sideways motion of galaxies across the sky. In addition to their radial velocities toward or away from us, these measurements reveal that Andromeda's approach is slightly off-center, with a significant tangential component that affects the timing and geometry of the eventual merger. The local group also serves as a laboratory for studying dark matter distribution and properties. By analyzing the orbital dynamics of satellite galaxies, astronomers can map the dark matter halos of the Milky Way and Andromeda with greater precision than possible for any other galaxies. These studies have revealed that dark matter halos extend far beyond the visible boundaries of galaxies and dominate the gravitational dynamics throughout the local group. Recent discoveries have expanded our understanding of local group boundaries and membership. The detection of extremely faint dwarf galaxies has revealed that the local group may contain several hundred small galaxies, most too dim to have been discovered until recently. Advanced survey techniques using digital cameras and sophisticated image processing continue to find new local group members at the edge of detectability. The local group's isolation in the expanding universe creates unique conditions for galaxy evolution, and like galaxies in rich clusters that experience frequent interactions and mergers. Local group galaxies have evolved in a relatively quiet environment dominated by the gradual approach of the two most massive members. This environment preserves features of galaxy structure and evolution that might be disrupted in denser cosmic environments. The study of local group dynamics also provides crucial tests of our understanding of dark matter and modified gravity theories. Alternative theories of gravity, such as modified Newtonian dynamics (MOND), make specific predictions about orbital dynamics in systems like the local group. Precise measurements of galaxy motions allow astronomers to test these theories against observations and constrain the properties of dark matter. The future evolution of the local group depends on the cosmic environment as well as internal dynamics. As cosmic expansion accelerates due to dark energy, the local group will become increasingly isolated from neighboring galaxy groups. Within roughly 100 billion years, all galaxies beyond the local group will have been carried so far away by expansion that they will no longer be visible to observers in our cosmic neighborhood. This cosmic isolation means that the local group represents humanity's permanent cosmic neighborhood, all the galaxies we can ever hope to visit or study in detail. Given the constraints of light speed and cosmic expansion, understanding the local group's structure and evolution thus becomes crucial for understanding our cosmic future and the long-term fate of structure in our region of the universe. The local group also provides a unique perspective on cosmic expansion itself. By studying how the group's boundary interacts with the expanding cosmic environment, astronomers can probe the transition between gravitationally bound and expanding regions. This boundary region experiences complex dynamics where expansion and gravity compete most directly. Advanced computer simulations now model local group evolution within the broader context of cosmic structure formation, revealing how our cosmic neighborhood formed through the merger of smaller dark matter halos over billions of years. These simulations predict the detailed orbital evolution of local group galaxies and help interpret observations of similar galaxy groups throughout the universe. The local group thus represents far more than just our cosmic address. It's a gravitationally bound laboratory where we can study galaxy formation, dark matter physics, and the interplay between cosmic expansion and local gravitational dynamics in unprecedented detail. The blueshifted galaxies in our neighborhood aren't cosmic anomalies but natural consequences of living within a bound structure where gravity has triumphed over expansion. Understanding our local group illuminates the hierarchical nature of cosmic structure and reveals how the universe organizes itself into bound islands of complexity within the expanding sea of space. Time. These islands preserve the gravitational legacy of the early universe while providing cosmic laboratories for studying fundamental physics in regimes that span from galactic to cosmological scales. Dark energies push deep beneath the obvious matter and energy that make up stars, planets, and galaxies lurks something far more mysterious and powerful: dark energy. an invisible component that comprises roughly 70% of the universe and drives the accelerating expansion that will ultimately determine the cosmic fate of every structure, including our local group. Understanding dark energy is crucial for comprehending why cosmic expansion doesn't affect all regions equally, and how blue-shifted galaxies can exist in an accelerating universe. The discovery of dark energy ranks among the most shocking revelations in the history of astronomy. For most of the 20th century, astronomers expected that cosmic expansion would gradually slow down due to the gravitational attraction of matter in the universe. The only question seemed to be whether the universe contained enough matter to eventually halt expansion and collapse back on itself, or whether it would expand forever at a decreasing rate. In the 1990s, two independent research teams set out to measure this cosmic deceleration by observing type Ia supernovae stellar explosions that can be used as standard candles to measure cosmic distances. These supernovae occur when white dwarf stars accumulate matter from companion stars until they reach a critical mass and explode with remarkably consistent brightness. By comparing their observed brightness with their intrinsic luminosity, astronomers can determine their distances with high precision. What the supernova teams discovered defied all expectations. Instead of slowing down, cosmic expansion was speeding up. Distant supernovae appeared fainter than they should have if expansion were decelerating, indicating that they were farther away than predicted by models of a matter-dominated universe. The universe wasn't just expanding, it was accelerating its expansion at an ever-increasing rate. This acceleration requires a new form of energy with properties unlike anything in our ordinary experience. Dark energy must have negative pressure; it pushes outward rather than pulling inward like gravity. As the universe expands and dark energy fills the new volume of space created by expansion, its repulsive effect grows stronger rather than weaker, driving ever faster expansion in a runaway process. Einstein's general relativity actually predicted this possibility through the cosmological constant, a term he added to his field equations to allow for a static universe. Einstein later called this his greatest blunder when Hubble's observations revealed cosmic expansion, but the cosmological constant provides the simplest explanation for dark energy. A constant energy density filling all of space would produce exactly the negative pressure needed to drive accelerating expansion. The mathematics of dark energy emerge from the equation of state that relates pressure to energy density. For ordinary matter, pressure equals 0 dust-like behavior, while for radiation, pressure equals 1/3 the energy density. Dark energy requires pressure equal to -1 times the energy density, creating the repulsive gravitational effect that drives acceleration. This repulsive nature of dark energy doesn't mean it pushes matter around directly. Instead, dark energy affects the geometry of spacetime itself, causing space to expand at an accelerating rate. Matter responds to this changing geometry by following geodesics through the expanding spacetime, creating the appearance of acceleration without any direct force acting on the matter. The onset of dark energy domination roughly 5 billion years ago marked a crucial transition in cosmic evolution. Before this transition, matter and radiation dominated the universe's energy budget, and gravitational attraction slowed cosmic expansion over time. The transition occurred when the matter density dropped below the dark energy density due to the expansion of space. Matter density decreases as volume increases, while dark energy density remains constant. This transition has profound implications for structure formation in the universe. During the matter-dominated era, density fluctuations could grow under gravitational attraction, forming the cosmic web of galaxies and clusters we observe today. After dark energy began dominating, structure formation became increasingly difficult as accelerating expansion works against gravitational collapse. The effect of dark energy on bound structures like our local group depends on the competition between dark energy's repulsive effects and gravity's attractive effects. For sufficiently massive and compact systems, gravity wins and structures remain bound. For less massive or more extended systems, dark energy eventually overcomes gravitational binding and tears structures apart. Current calculations suggest that structures with masses above roughly 10 solar masses, typical of large galaxy clusters, will remain bound indefinitely in a universe with constant dark energy density. Smaller structures face more uncertain fates, though groups like our local group appear massive enough to remain stable throughout cosmic time. The nature of dark energy remains one of the deepest mysteries in physics. The simplest explanation, Einstein's cosmological constant, faces the notorious fine-tuning problem. Quantum field theory predicts that vacuum energy should contribute to the cosmological constant. But at a level 120 orders of magnitude larger than observed, this represents perhaps the worst theoretical prediction in the history of physics. Alternative theories propose that dark energy might be dynamic rather than constant. Quintessence models suggest that dark energy could be a slowly evolving scalar field that changes its properties of our cosmic time. Phantom dark energy could even grow stronger over time, eventually overcoming all gravitational binding and tearing apart every bound structure in the universe in a Big Rip scenario. Modified gravity theories offer another approach to explaining cosmic acceleration without invoking dark energy. These theories suggest that Einstein's general relativity might break down on cosmic scales, requiring modifications that naturally produce repulsive gravitational effects. However, most modified gravity theories struggle to explain cosmic acceleration while remaining consistent with other gravitational observations. The measurement of dark energy's properties has become one of the primary goals of modern cosmology. Large-scale surveys like the Dark Energy Spectroscopic Instrument DESI and the upcoming Euclid SPA mission will measure the expansion history of the universe with unprecedented precision, potentially revealing whether dark energy is truly constant or evolving over time. These observations will also test whether dark energy interacts with matter in ways beyond its gravitational effects. Some theories suggest that dark energy might couple directly to dark matter, affecting structure formation in ways that could be detected through precise measurements of cosmic structure growth over time. The cosmic implications of dark energy extend far beyond academic curiosity. If dark energy remains constant, the universe will expand exponentially in the far future, with all matter beyond our local group eventually becoming invisible as it gets carried beyond the cosmic horizon. If dark energy grows stronger, it could eventually overcome all forces in nature, leading to the complete dissolution of all structure. Understanding dark energy also connects to fundamental questions about the nature of empty space and the quantum structure of spacetime itself. The energy density of dark energy approaches the scale where quantum gravitational effects might become important, suggesting potential connections to theories of quantum gravity and the fundamental structure of reality. The study of blueshifted galaxies in our local group provides crucial context for understanding dark energy's effects. These galaxies demonstrate that dark energy doesn't uniformly affect all regions of space. Its effects can be completely overcome by sufficient matter density and gravitational binding. This reveals that dark energy operates as a background effect that influences cosmic geometry while allowing local gravitational dynamics to proceed normally in bound systems. Dark energy thus represents both cosmic destiny and cosmic mystery, the dominant component of our universe whose nature remains fundamentally unknown. Its discovery through cosmic acceleration measurements revolutionized cosmology while creating new puzzles that may require revolutionary advances in fundamental physics to resolve. The push of dark energy shapes the cosmic stage on which the drama of gravitational binding and cosmic expansion plays out, determining which structures survive and which succumb to the accelerating expansion of space itself. Measuring motion. The precise measurement of how fast galaxies move toward or away from us represents one of the greatest technical achievements in astronomy, requiring observations that can detect wavelength shifts smaller than the width of individual atoms while extracting signals from sources so distant that their light has traveled for millions or billions of years to reach our telescopes. These measurements provide the foundation for understanding cosmic expansion, local gravitational dynamics, and the mysterious blueshifts that challenge our basic assumptions about how the universe works. The fundamental tool for measuring galactic motion is spectroscopy, the detailed analysis of light broken down into its component wavelengths. Every chemical element produces a unique spectral fingerprint when it emits or absorbs light, creating patterns of bright or dark lines at specific wavelengths determined by quantum mechanics. These spectral lines serve as cosmic rulers, allowing astronomers to measure even tiny changes in wavelength that reveal motion through space. The most important spectral features for velocity measurements come from hydrogen, the most abundant element in the universe. The Lyman series in the ultraviolet and the Balmer series in the visible spectrum provide strong, easily identified lines that appear in virtually every galaxy spectrum. The 21-centimeter radial line of neutral hydrogen offers another powerful probe, particularly useful for studying the outer regions of galaxies where optical light becomes too faint to observe. Modern spectrographs can measure wavelength shifts with extraordinary precision, detecting velocity changes as small as a few meters per second slower than a typical walking pace. This precision requires careful calibration using laboratory light sources and sophisticated techniques to account for Earth's motion through space, atmospheric effects, and instrumental systematic errors. The challenge of measuring galactic velocities extends beyond simple technical precision to fundamental questions about reference frames and coordinate systems. When we say a galaxy is moving toward or away from us, we must specify what this means in the context of cosmic expansion. Are we measuring motion relative to Earth, the solar system, the Milky Way, or some cosmic reference frame? The most meaningful reference frame for cosmological studies is the cosmic microwave background (CMB), the afterglow of the Big Bang that provides a universal reference frame for motion through the universe. Our local group moves at roughly 630 kilometers per second relative to the CMB rest frame, heading toward the constellation Hydra. This motion must be subtracted from observed galaxy velocities to determine their motion relative to the cosmic expansion flow. The measurement of peculiar velocities' motions relative to the cosmic expansion reveals the complex gravitational dynamics that operate within the cosmic web. These peculiar velocities can be quite large. Our local group's motion relative to the CMB reflects gravitational attraction toward the Virgo cluster and the even more massive Shapley supercluster Bayo. ND. Understanding these motions helps map the distribution of matter throughout the universe, including dark matter that can only be detected through its gravitational effects. For nearby galaxies like those in our local group, peculiar velocities often dominate over cosmological recession velocities, creating the blueshifts we observe. Andromeda's approach at 300 kilometers per second toward the Milky Way completely overwhelms the expected cosmological recession of roughly 70 kilometers per second at its distance, resulting in a net blueshift that reveals the strength of gravitational binding within our cosmic neighborhood. The interpretation of velocity measurements becomes increasingly complex from more distant galaxies, where cosmological expansion begins to dominate over local gravitational effects. At distances beyond about 100 million light-years, most galaxies show redshifts consistent with cosmic expansion, though significant peculiar velocities can still affect individual measurements. Advanced observational techniques have revolutionized our ability to measure three-dimensional galaxy motions. Traditional spectroscopy reveals only radial velocities motion toward or away from us along the line of sight, but the Hubble Space Telescope's exquisite resolution allows measurement of proper motions, tiny sideways motions across the sky for nearby galaxies like Andromeda and the Large Magellanic Cloud. These proper motion measurements provide crucial information about orbital dynamics within the local group. Andromeda's proper motion reveals that its approach to the Milky Way isn't perfectly head-on but includes significant sideways motion that affects the timing and geometry of the eventual collision. These measurements allow astronomers to reconstruct the orbital history of local group galaxies and predict their future evolution. The Gaia spacecraft has revolutionized proper motion astronomy by measuring the positions and motions of over 1 billion stars in our galaxy with unprecedented precision. While Gaia can't directly measure proper motions of external galaxies, it provides crucial information about the motion of nearby satellite galaxies and helps establish the precise reference frame needed for interpreting other velocity measurements. Statistical techniques become crucial for extracting meaningful information from large samples of galaxy velocity measurements. Individual galaxies have complex motions influenced by local gravitational interactions, but averaging over many galaxies reveals the underlying patterns of cosmic expansion and large-scale gravitation. Outflows. These techniques have revealed vast streams of galaxies flowing toward massive attractors like the Great Attractor, a concentration of mass that influences galaxy motions over hundreds of millions of light-years. The measurement of galaxy velocities also provides crucial tests of cosmological models and theories of structure formation. Computer simulations of cosmic evolution predict specific patterns of galaxy motions based on the assumed properties of dark matter and dark energy. Comparing these predictions with observed velocity patterns allows astronomers to constrain cosmological parameters and test theories of cosmic structure formation. Recent advances in spectroscopic surveys have enabled velocity measurements for millions of galaxies, creating three-dimensional maps of cosmic structure with unprecedented detail. The Sloan Digital Sky Survey and its successors have measured redshifts for over 4 million galaxies, revealing the cosmic web's intricate structure and providing precision tests of cosmological models. Future surveys will push these measurements to even greater precision and larger scales. The Dark Energy Spectroscopic Instrument DESI will measure velocities for 35 million galaxies and quasars, while space-based missions like Euclid will combine velocity measurements with precise shape measurements to probe the effects of dark energy and dark matter on cosmic structure. The interpretation of velocity measurements continues to reveal new physics and challenge our understanding of cosmic dynamics. Recent measurements suggest that the local expansion rate of the universe, the Hubble constant, differs from the value inferred from cosmic microwave background observations. This Hubble tension might indicate new physics beyond the standard cosmological model or could reflect systematic errors in distance measurements. The study of satellite galaxy motions within the local group has revealed another puzzle. These galaxies appear to orbit in a thin plane around the Milky Way, rather than being randomly distributed as expected for dark matter subhalos. This unexpected behavior challenges our understanding of galaxy formation within dark matter halos and might indicate previously unknown physics of dark matter or galaxy formation. Modern velocity measurements thus provide windows into cosmic dynamics across scales from the local group to the largest structures in the universe. These measurements reveal the complex interplay between cosmic expansion, gravitational attraction, and dark energy that shapes cosmic evolution. The blue-shifted galaxies in our neighborhood represent just one facet of this cosmic dynamics, demonstrating how precise velocity measurements continue to challenge and refine our understanding of the universe's structure and evolution. The future of galactic velocity measurements promises even greater precision and new discoveries as improved instruments and analysis techniques reveal previously hidden aspects of cosmic motion. Each measurement adds another piece to the cosmic puzzle, bringing us closer to understanding the fundamental nature of space-time, gravity, and the mysterious dark components that dominate our universe. Cosmic web. The universe on the largest scales resembles a vast spider web, with galaxies and galaxy clusters arranged along luminous filaments separated by enormous dark voids where almost no matter exists. This cosmic web represents the largest scale structure in the universe, shaped by billions of years of gravitational evolution as matter flows from low-density regions into high-density nodes where cosmic expansion loses its battle against gravity. Understanding this web illuminates why some regions host blue-shifted galaxies while others participate fully in cosmic expansion. The cosmic web emerges from the interplay between cosmic expansion and gravitational attraction operating over vast scales and cosmic time. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly throughout space, with only tiny density fluctuations seeded by quantum mechanical effects during cosmic inflation. These minute variations, detected in the cosmic microwave background radiation, provided the gravitational seeds from which all cosmic structure grew. As the universe expanded and cooled, regions with slightly higher density expanded more slowly than the cosmic average, while regions with lower density expanded faster. This process amplified the original density contrasts over time, with matter gravitationally flowing from underdense regions toward overdense regions. After billions of years, this flow sculpted the cosmic web we observe today. The mathematical description of cosmic web formation involves the gravitational instability theory developed by James Jeans in the early 20th century and extended to expanding universes by Evgeny Lifshitz and others. Small density perturbations grow exponentially under gravitational attraction until they become nonlinear, at which point complex dynamics take over and structures begin collapsing to form dark matter halos that eventually host galaxies. Computer simulations of cosmic structure formation reveal the intricate process by which the cosmic web develops. These simulations follow the gravitational evolution of billions of dark matter particles from the early universe to the present day, revealing how tiny initial fluctuations grow into the complex network of filaments, nodes, and voids we observe. The Millennium simulation and its successors demonstrate that cosmic web formation follows universal patterns determined by the properties of dark matter and dark energy, regardless of the specific initial conditions. Gravitational evolution produces similar web-like structures with characteristic features, hence nodes where multiple filaments intersect, elongated filaments connecting the nodes, thin sheets or walls where filaments merge, and vast voids with very little matter. The cosmic web operates on a hierarchy of scales, from the local group to the largest observable structures spanning billions of light years. Our local group sits within the local sheet, a flattened structure roughly 7 million light-years thick and 100 million light-years across that contains several dozen galaxy groups. The local sheet forms part of the Virgo supercluster, which in turn belongs to the even larger Laniakea supercluster spanning 500 million light-years. These nested structures reflect the hierarchical nature of gravitational collapse in an expanding universe. Smaller structures form first and then gradually merge to create larger systems, with the most massive structures still growing today through the accretion of matter from surrounding regions. This ongoing assembly process creates the complex motions we observe as galaxies flow along filaments toward massive nodes in the cosmic web. The discovery of the cosmic web required decades of painstaking galaxy surveys to map the three-dimensional distribution of galaxies throughout space. Early surveys like the CFA Redshift survey revealed the first hints of large-scale structure, including the famous Great Wall of Galaxies stretching across hundreds of millions of light-years. Subsequent surveys have mapped increasingly large volumes of space, revealing cosmic web structure out to distances approaching the edge of the observable universe. The Sloan Digital Sky Survey represents one of the most ambitious mapping projects in astronomy, measuring distances and positions for millions of galaxies to create detailed three-dimensional maps of cosmic structure. These maps clearly show the cosmic web's filamentary structure, with galaxies arranged along thin threads separated by vast regions containing very few galaxies. The cosmic web structure directly affects galaxy formation and evolution. Galaxies that form within the dense nodes of the web, such as those in massive galaxy clusters, experience frequent interactions and mergers that can trigger star formation, strip away gas, and transform spiral galaxies into elliptical ones. In contrast, galaxies in less dense environments like cosmic filaments or voids evolve more quietly and can maintain their original spiral structure for billions of years. Our local group occupies a relatively quiet region within the cosmic web, connected to larger structures through tenuous filaments but isolated enough to evolve without major disruptions. This environment allowed the Milky Way and Andromeda to develop as large spiral galaxies while maintaining their satellite systems and preparing for their eventual merger. The cosmic web also governs the large-scale flows of matter throughout the universe. Galaxies don't simply participate in cosmic expansion, they also move through space under the gravitational influence of the web's massive structures. These peculiar velocities can be quite large, with entire galaxy clusters moving at hundreds of kilometers per second toward regions of higher matter density. The Great Attractor represents one of the most dramatic examples of cosmic web dynamics. This massive concentration of matter, located roughly 250 million light-years away behind the disk of our galaxy, exerts gravitational attraction on galaxies across a vast region. Our local group participates in this flow, moving toward the Great Attractor at roughly 630 kilometers per second relative to the cosmic microwave background rest frame. Even more remarkable is the discovery that the Great Attractor itself is being pulled toward an even more massive structure, the Shapley supercluster, located roughly 650 million light-years away. This hierarchy of gravitational attraction extends across the largest scales in the universe, with matter flowing from smaller structures into progressively larger ones according to the cosmic web's architecture. The cosmic web's influence on galaxy motions helps explain the complex velocity patterns observed in our cosmic neighborhood. While cosmic expansion provides the overall background, the web's gravitational structure creates additional motions that can either enhance or oppose the expansion flow. In regions where multiple filaments converge, these additional motions can be large enough to overcome expansion entirely, creating the gravitational binding that produces blueshifted galaxy groups like our local group. Dark matter plays the dominant role in cosmic web formation and evolution. The visible galaxies we observe represent only the tip of the iceberg. They trace the much more massive dark matter structures that provide the gravitational scaffolding for the entire web. Dark matter halos can extend far beyond the visible boundaries of galaxies, creating extended regions of gravitational influence that affect the motions of neighboring galaxies. The cosmic web's evolution continues today and will persist far into the future, though dark energy's acceleration of cosmic expansion affects this evolution in complex ways. As expansion accelerates, it becomes increasingly difficult for matter to flow along filaments toward massive nodes. Eventually, cosmic acceleration will overcome the gravitational forces that drive cosmic web formation, leading to a universe where bound structures become increasingly isolated from each other. Current research focuses on understanding how dark energy affects cosmic web evolution and structure formation. Precise measurements of galaxy motions within the web provide crucial tests of cosmological models and constraints on the properties of dark energy, discrepancies between observed and predicted structure growth rates might indicate new physics beyond the standard model of cosmology. The cosmic web also connects to fundamental questions about the nature of space and time on the largest scales. Some theories suggest that the web's structure might reflect deeper geometric principles related to the topology of space itself. Understanding these connections could provide insights into the fundamental nature of spacetime and its relationship to matter and energy. Future surveys will map the cosmic web with unprecedented detail, potentially revealing new aspects of large-scale structure and cosmic evolution. Projects like the Dark Energy Spectroscopic Instrument and the Euclid Space Mission will measure positions and velocities for tens of millions of galaxies, creating three-dimensional maps that span most of the observable universe. The cosmic web thus provides the largest scale context for understanding why some galaxies are blueshifted while others follow cosmic expansion. The web's complex gravitational architecture creates regions where expansion dominates and regions where gravitational binding prevails, determining which galaxies approach each other and which participate in the general cosmic expansion. Our local group's position within this vast web explains both our cosmic destiny and our current observations of blue-shifted neighboring galaxies.